All right, good. So now we're recording. Before we finish up our discussion of shapes and polarity and hopefully bring this section to a close, we will have an exam on Wednesday coming. So we'll have an exam on Wednesday coming. Lord willing, everyone's going to be back or can be back in person for the exam. If that is not the case, just let me know, and we'll have an online version available. So we'll work around whatever your needs are. But in a perfect world, we'll all be here and sit and take it. We'll talk about it at greater length on Monday, but if I don't mention it today, I'll forget it completely. Probably about 15 questions. It will be predominantly short answer. I generally write the exam and then drop a question to make sure that it's not too long. Okay, and it will cover whatever we cover through close of class today. We will lecture on Monday on new material, but it will not be on Wednesday's exam. Okay? All right. So let's go back one last time here and let's look at VSEPR steric number model electronic geometry. Steric number 4 is that tetrahedral. Don't have the toys out this morning, but I think we've seen them enough that hopefully we can get that picture in our heads. Again, those are the three that we will see most often. Again, there's the problem with it being that low. The glare is bad. Oh well, we'll hope people can see it on the recording as necessary. The other two cases that we deal with are 5 and 6. With 5 groups around the central atom, again, this is trigonal, this is the ugly one, bipyramidal. And then finally with the steric number of 6, what is called octahedral, if I can spell the word. I want to sweep through this quickly one more time. I want to add one more extension to this just to add to our descriptive language. I hope I don't sow confusion. I hope I just give you another way of thinking about this, but it involves extending our quantum theory. And then we'll move on to greener pastures of interparticle forces, which, again, you've done some lab work on that, and that's fine. Now, so we've got this polarity, okay? So polar molecules, polar bonds, means we have a difference in electronegativity. And polar molecules are going to have, they will contain polar bonds. So polar molecules have polar bonds. And some sort of asymmetry. That is to say, in some form or fashion, it will be unbalanced electronically. again, and if I can remember who told me we'd use their name, but I had a student that said, it's the and thing. If it's got a steric number 4 and it's connected to the 4 of the same things, then it's going to be non-polar. Hey, it's connected to 4 hydrogens. That means it's symmetric. But if it's connected to 3 hydrogens and has a lone pair, okay, the and is going to make it asymmetric. Okay, so can I come up with an exception? Yeah, but we don't test the exceptions. We try and test the rules. Okay, so the bottom line is, if we are looking at a structure and saying, okay, it's got a certain number of 5, the only way that's going to be non-polar if it contains polar bonds. So if we give that it contains polar bonds, it's got a certain number 5. All 5 bonded atoms have got to be. If they've all got to be bonded atoms, they've all got to be the same. Okay. And again, the back of my head has already got the exception to that rule, but that's fine. Okay. With octahedral, again, at least on the surface, unless they're all 6 the same or one easy case I'll talk about, it's going to be polar in some form or fashion. If it's 5 groups and a lone pair, if that's a lone pair out here, that's going to make it polar. If there are 2 lone pair, they happen to, if they're still lone pair, they're always going to put themselves opposite each other, and that leaves a square, which means that would be nonpolar. But that's an exceptional case. If something like that were to show up on the exam, it would show up as a bonus question and not as a, difference between an A and a B question. Okay. Here's what's going to happen. I'm going to give you a structure, say something that looks like this. And say, okay, great. Steric number on the sulfur. Electronic geometry. Molecular geometry. I like to use the word shape when I'm talking about the molecule. Polar or non-polar. There's one other thing I'll ask you, we'll cover that today, but there's one other thing I'd ask. So we say, great, so what's the steric number on that central sulfur? 3, okay? 2 oxygen atoms, 1 lone pair. So with the steric number of 3, the electronic geometry is going to be then trigonal, triangular, planar. Okay. This information needs to be yours. These 2 columns that are on the board right there. The molecular geometry, what's the molecule shaped like? So let's draw it. So, okay, great. I've got this. So there's my triangle. Sulfur's in the center. The 2 oxygens are at 2 points, and the lone pair's at the 3rd point of the triangle. But the shape of the molecule would then be simply bent. We'll just call that bent. If you want to say non-linear, that's what the word bent means, but that's fine, non-linear. So now, is it polar or non-polar?
Polar.
It's polar because?
Has a lone pair.
Yeah, the lone pair. Okay. Again, these bonds are polar toward the oxygens. Okay. So again, in general, this is the negative end, that's the positive end. Or you can simply say, hey, what's it connected to? 2 oxygens and a lone pair. Okay, it's polar. I would also tell you this, if it contains polar bonds and it's bent, it's got to be polar, because bent means it's not completely symmetric. Okay. We have done this sort of thing piecemeal for a lot of other examples. So go back and pull those examples out of your notes and look and say, okay, great. So if he asks me about this molecule, can I answer all of those questions about it? And that's what I'm going to ask. Hey, here's a Lewis structure. steric number, electronic geometry, molecular geometry, polarity. The other thing I'm going to ask, and this is our last excursion into I better just say next, or this is going to be an excursion back into quantum mechanics and talk about why regular quantum mechanics don't work for this and why we have to adapt it. Okay? So I'm going to erase just this half of the board. I'm going to leave that up there for a little bit longer. Is this all right? May I erase? Okay. Let's consider methane. There's methane. There's the Lewis structure. The steric number on the carbon is 4. And so we would argue that the geometry should be, and when we look at the molecule in the real world, the geometry is this tetrahedral geometry. Okay. Carbon is on row 2. So the electronic orbitals that are available to it, its outside electrons, its valence electrons are going to be 2s and 2p. Okay? So 2s can hold 2 electrons, 2p can hold 6 electrons. Okay? 3 boxes, 2 per box. Carbon has a valence of 4. So it's going to provide 4 of the electrons to put in these boxes. The hydrogens each provide 1. So there's the other 4, there's 8. Okay? So when it's all said and done, I would argue that the molecule is going to have that occupation. The molecular orbital occupation, if we're dealing with pure atomic orbitals. 2s is going to be filled, 2p is going to be filled, that's the octet. Okay, that meets our expectations, we're happy. Here's the problem. The 3p orbitals in this p sublevel, I'm going to write out the word 3 so you don't think it's 3p, because it's the 2p orbitals. These 3p orbitals are at 90-degree angles. The bond angle in tetrahedral is 109.5 degrees. The 3 pure p orbitals are at 90-degree angles. Okay? Tetrahedral angles are 109.5 degrees. And at the risk of being 90 does not equal 109.5. Pure atomic orbital theory will not explain these shapes. And I'm just going to tell you it doesn't explain any of them. Octahedral we can play and get close. But the other ones you're going, we can't rationalize all of that. Okay? So what we have to do is adapt our orbital theory, and we're going to use what are called hybrid orbitals. Okay, I'm going to give you 2 examples of a hybrid. I'm going to just tell you with the pen held in my hand and not writing on the board what we do mathematically, and then I'm just going to tell you what the results are and what we call them. I don't want to drag you down into the abyss where I love to live. Okay, but here we go. Since we had children, we've had 2 dogs at my house. Most recently, a purebred Shih Tzu who weighed all of about 12 pounds and ran the other dog rabid. Okay, the other dog was half Shih Tzu and half Red Heeler. Okay, so you can only imagine what that dog might have been like. Okay, he would herd the children when they were young, and then demand to be picked up because he really thought he was still a lap dog. In his head, he was both. He had stand-up ears like a Heeler, except they flopped over and had long hair like a Shih Tzu. Okay. He had a long flowing coat, but when we'd cut him for the summer, you could see all the spots on his hindquarter, like you expect on the back of a Heeler. He had the short face of the Heeler with the round eyes, but didn't have the underslung jaw. He was he was a hybrid. Did he look like a Heeler or did he look like a Shih Tzu? Yes. Did he act like a Heeler or did he act like a Shih Tzu? Yes. So he was a hybrid. He was a mixture of those two. Okay? So you understand that idea, particularly of genetic hybrids. Okay, that's fine. That's within our experience. If we're going to do barbecue, we're going to do it correctly, that means we need to put together a good spice rub. And we want all 4 of our briskets or pork butts, whichever one we're doing. We're doing pork at my house this weekend, so let's go with that. We want all 4 pork butts to be spiced the same. So we wouldn't spice one of them with just pure salt and the other 3 with just pure pepper. They wouldn't be the same. And so what we would do to start is take a cup of salt, 3 cups of pepper, put it in a bowl, stir it around, and then scoop even cups back out. And now each of those would be 1 part salt and 3 parts pepper. Of course, there would be cumin and paprika and all the other stuff, but let's just deal with salt and pepper. And now when I rub that pork, they're all going to be exactly the same. Okay? If we think of these electron orbitals, and quantum mechanics tells us to, as waves, and we express those as mathematical functions, then we can make what are called linear combinations. That just means add and subtract. But we can make 4 linear combinations of the S and the P orbital sets and generate 4 equivalent, same energy, same shape orbitals. And when we do that mathematically, do you know what shape those orbitals take? Tetrahedral. So what we do is we describe these. We say, okay, great, we're going to take this and we are going to quote unquote hybridize. Think of it this way, mix. Spices is still the best way I can think about it because it's exactly what we do. If I've got 1 cup of salt and 3 cups of pepper, I want to make even spice mixtures. I know what I do, pour them in a bowl. Take the whisk them up, pull them back out. Now I've got 4 cups that are 1 part. I've got 4 then that are exactly the same, and they're 1 part salt and 3 parts pepper. And we call these sp3 hybrid orbitals. If something has a steric number of 4, we will say that atom is sp3 hybridized. Now, if you say that, sp3, so how many is that? That's 4. What's the steric number? 4. So what does sp3 mean? Steric number 4. What does number 4 imply with regards to hybridization? sp3. So I'm going to take all 4 of these orbitals and hybridize them and come up with 4 equivalent sp3 hybrids. Not only does the math then give us 4 energetically equivalent orbitals, they orient themselves, the math makes them tetrahedral. And that matches our reality. So what we've done is just to adapt our quantum theory to say orbitals can mix to form these combinations. And you're going, well, I didn't fully understand quantum mechanics when we covered it, and I'll just add that to my box of things I don't fully understand. Okay? And by the way, I have a PhD, and I still have to chew my way through some of this stuff as well. Okay? If it really interests you, come to my office and we'll pull the math out and do the calculations. And now that will keep any of you from ever coming by my office to discuss quantum mechanics. All right? Now, sticking with carbon. So when carbon has a steric number 4, it's tetrahedral, it's sp3 hybridized. So that means the last question, remember we had steric number, electronic geometry, molecular geometry, polarity, and then I would ask hybridization, okay? If the steric number is 4, then the hybridization is sp3. It involves all 4 of my molecular orbitals, the s and all 3 of the p's. But we're going to mix them and come up with 4 equal ones. Let's continue the game. So we need to find the steric number on this carbon, the electronic geometry, the molecular geometry, the polarity, and we'll just say what the hybridization is and talk about the one other thing going on here. It's going to make us look at bonding one more time. Okay, so steric number on the carbon is 3. There are 3 things attached. So the electronic geometry is trigonal planar. And the molecular geometry, since they're all atoms, is trigonal planar as well. Now, is this molecule polar or nonpolar? It's polar because 2 hydrogens and oxygen, so it's polar. Now, how many atoms are we bonding? 3, okay? There are 3 bonded atoms. One of those atoms is doubly bonded, and we haven't talked about how that second bond gets made. And that's where we are right now. But I want to bond 3 things. So how many equal orbitals do I need? I need 3 equal orbitals. Okay, because I'm going to bond 3 things. That second bond there on the oxygen is something new. Okay, we haven't discussed that. That's something new, but I'm going to need to make 3, what I'm going to call right now, simple bonds, and then I'm going to make the double bond. Okay, so here again was carbon, 2s, 2p. I'm going to take 3 of those and hybridize them and make what are called sp2 hybrids. That leaves one pure, unhybridized p orbital. So the hybridization here is going to be sp2. Look, sp2, how many is that? 3. What's the steric number? 3. So again, if the hybridization hasn't really fully settled in yet, I don't really understand that. Okay, remember this. What does sp2 imply? Steric number of 3. What's sp3 imply? Steric number of 4. When we get to steric number of 2 here in a second, you're probably going to tell me what the hybrid label is without... Okay, let's just say. So if sp3 is sp3, that's steric number 4, and sp2 is a steric number of 3, what's a steric number of 2 going to be? Sp. Okay, you now have your hybrid labels. Sp, steric number of 2. Sp2, steric number of 3, sp3, steric number of 4, because there's s and 3 p's. So that's 4 things. Okay? Now, hybrid orbitals can only make what I put my hand quotes up and said, simple bonds. Okay? We're going to find out that there's 2 ways that orbitals can overlap by valence bond theory. We talked about this at all first term. I know that's been a year ago. Yeah, I've forgotten too. Obviously, I wouldn't be asking. So let's quickly talk about bonding theory. We have 20 minutes. We're going to be home here, okay? And we'll be done with this. So let's talk about this. Time for this to be erased. You can look that up in your notes. Okay. There are 2 fundamental flavors. Put this here. There are 2 fundamental flavors that bonds come in. Or there are 2 fundamental flavors that bonds come in. There are 2 fundamental theories to explain that. One of these is what's called valence bond theory. And it says very simply this: a bond forms when half-filled orbitals overlap. A bond forms when half-filled orbitals overlap. So here's one hydrogen, here's another hydrogen. That's a 1s, 1s1. There's one electron, the little dot, inside that orbital. And valence bond theory says, hey, they get close enough, they approach each other, and they overlap. And that's my bond. Okay, that makes good sense. Just talking physical space. Why are they bonded to each other? Because their electrons are being shared. It's covalent bond, valence bond theory. That's all fine and good if we're dealing with s orbitals. Let me show it to you here with HF. 1s1. The outer shell on fluorine is 1s2, 2p5. So there's 1s. It's got 1 electron in it. Here's fluorine. Two s. 2p. So there is the half-filled orbital on hydrogen, and there's the half-filled orbital on fluorine. So here's hydrogen. I'm just going to put the letter for the center of for the nucleus. There's the hydrogen with its electron. And here's the fluorine. So that's 2p, that's 1s. And what is valence bond theory? How do we explain the bond in HF? Those two just overlap so that I get this sort of picture. And there's my bond. Notice what's left on fluorine is 1, 2, 3 pairs. There's the 3 lone pair. What's left on hydrogen is nothing else, so it just makes the bond. So this idea of valence bond theory and Lewis structures, they go nicely hand in hand. One other example of this quote unquote simple type of bonding before we just apply it to hybrid theory here really quickly. Fluorine bond, F2. Okay, molecular fluorine. Each of the fluorines has an unpaired, half-filled 2p orbital. That was kind of funny. She probably thinks I was bad-mouthing healers earlier. I would not. Finest dogs. Okay, they're going to overlap. So again, that bond would be explained by just overlap of those 2p orbitals. Here's S and S, okay? They approach, they overlap, they bond, okay? This is how I do a p orbital, so you can see one end to the other. Here's S, it overlaps p, they overlap, they bond. Here's P and P. They overlap, they bond. Okay, nothing fancy there. Here's what I would point out. In each of these cases, let's notice if I draw a line between the nuclei, the shared space, okay? The shared space, that is to say, the bond, lies on the line of nuclear centers. If there were an easier way to say that, I might say it, but it takes 3 sentences to say that any other way. When we look at the bond and we look from nuclei to nuclei, we're looking right through the bond. Easiest way is for me to draw it. Where is that bond? Directly between the 2 nuclei. We call this is a sigma, and that's a lowercase sigma. This is a sigma bond. What I like to call, it's a head-on collision. This is head-on overlap. Remember where we started. How does a bond form? Half-filled orbitals overlap. If it's head-on like this, we call it a sigma bond. Okay? That's a sigma bond. So head-on overlap of atomic or hybrid orbitals. Single bonds are sigma bonds. Anytime 2 atoms bond, there is one and only one sigma bond. Anytime 2 atoms bond. So if I look at this molecule, that's 1, 2, 3 sigma bonds, because there are 3 occasions where carbon is bonded to something else. Just to make sure, sorry, people watching online, make sure you can get back to this. Okay? I'll duck. Anytime 2 atoms bond, there's one sigma bond. There's one sigma bond. Which begs the question then. So I'll ask it. Hey, Dr. Rogers, so that double bond, one of them sigma, what's the other? Well, for right now, it's not sigma. By the way, what have we used for this simple bond? The Greek letter for S. What's our simplest orbital? S. The second type of bond is going to, again, mirror that. So instead of, we're going to call it a pi bond. So the Greek letter for the same sound that we use for P. So pi. Okay? A pi bond. So that is a sigma bond. Oh, sorry, and sigma bond lies on the line of nuclear centers. A pi bond is side to side overlap of half-filled pure p orbitals. Here's my God-given electronic orbitals, okay? Here is P and P. They can overlap two different ways. Head on and form a bond, okay? Or they could hit side to side and overlap that way and form a bond. Let's draw the picture. If these two approach each other, then I can get something that looks like this, okay? And this is a pi bond. It's side-to-side overlap. Hey, where is the bond? It's not directly between the nuclei, is it? If I draw a line from nucleus to nucleus, does it go through the shared space? No. So a pi bond lies off the line of nuclear centers. Okay. Pause here for just a second. Is it going to cause anyone real grief if we delay the exam from Wednesday to Friday of next week?
Not one bit.
Okay. Cool. Because we've got 5 minutes left, and I've got about 40 minutes worth of stuff to finish up bonding theory. So we'll finish up this first exam on Monday. Wednesday we'll give a little more information. We'll do a little more lecture. It won't be on Friday's exam. The exam will not be on Wednesday. That's Wednesday is the 16th.
Oh,
Today is the 11th.
yeah.
So a week from today is the 18th. So the exam, rather than being the 16th, is now the 18th. Okay? I hope that doesn't mess with my schedule. It doesn't matter. It doesn't mess with yours, and that's what's important. Okay, so orbitals can overlap head-on. That's sigma. Single bonds are sigma bonds. Anytime two atoms bond, there's one sigma bond, period. Dr. Rogers, there's two bonds. What's the second one? If one of them's sigma, the other one has got to be pi. Okay? I'll draw pictures here. We've got 4 minutes left. Here's the other thing I would tell you. In multiple bonds, there is one sigma The others are pi. If I have a multiple bond, and in formaldehyde over there we do, one of those is sigma, and in the case of a double bond, that means 1 sigma and 1 pi. I encourage you between now and Monday, okay, crack open the textbook where there are professionally rendered computer graphics, okay, of hybrid orbitals, their shapes, and sigma and pi bonds, okay? Do not rely on this lecture solely, okay? Pop open your book, Khan Academy, YouTube. There will be actually some animated video stuff that moving can show you at the orbitals approaching, overlapping each other. Tro's graphics are excellent, I think, with regards to showing bond overlap. Okay, so I encourage you strongly between now and Monday to do that. If I look here, these carbons have a steric number of 3. Each of the carbons has a steric number of 3, and therefore are sp2 hybridized. There are the sp2 hybrids. Okay? Here is carbon. There's the other one. Notice that sigma, because it's on that line, sigma, it's on the connecting line, sigma, it's on the connecting line, sigma, sigma. When I draw between the nuclei, I run through those bonds. Okay? If carbon is sp2 hybridized, that means it has 1 pure p orbital left over. So here is the p orbital on one carbon. There is the p orbital on the other carbon, and they can overlap side to side. So this is the pi bond. It's above and below that line of nuclear centers. These ones that I've got with the dirty orange now, because I dragged it through the blue, those are sigma. So let's take the red pen and let's come up here and label this. Sigma, 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 1 sigma, 1 pi. So the 6 bonds there in ethene. Okay? There are 1, 2, 3, 4, 5 times that one atom is bonded to another. That means there's 5 sigma bonds, period. There's a 6th bond, Dr. Rogers. What is it? Well, if it's not sigma, it's pi. We're out of time today. What we will do on Monday is come back. We'll look at a couple of other examples of sigma and pi and get you to a working knowledge. We will have to dabble a little bit in molecular orbital theory, which is a deeper mathematical treatment, but we will get to the results as quickly as possible and not drag you through too much math. All righty? Okay. Hey, 3 weeks in, and everybody is still healthy and alive, and I praise God that that is true, and our case count is low, and Lord willing, He lets us finish the rest of the term. Have a good weekend.